So Unit 5, Chapter 2, we are going to kind of continue with some of the naming that we are, but instead of naming just the ions like we ended Chapter 1 with, we're going to now look at naming the compounds in which those ions come to form. And there'll be a few examples. We will be going in and out of using the periodic table and some of the with that. So I would highly suggest having your periodic table handy so that you can understand and follow what I am doing and where I'm getting some of this stuff. So one of the big things that we need to understand is that all chemical compounds are neutral. That means the number of positives need to equal the number of negatives. The cations need to equal the number of anions. How that's done is a way, there's a couple different methods. We'll show both of them. And then and one of the methods is one that's a little bit more widely used than the other. But ultimately, we need to understand that the positives need to equal out the negatives. So they need to be neutral, and so that means no charge. So when writing the formula for an ionic compound, we have two steps. I've tried to keep these steps as simple as possible, so I highly suggest not trying to simplify them any more, as then you would oversimplify things, and that can sometimes come back and bite you, and we don't want that. So the first step is to write the formula for the cation. That's usually the metal as well, and then followed by the formula for the anion. That's usually the non-metal. And so you're going to be writing the formula for the positive. It's kind of like, hey, give me my positive information first before you find out the negative. And so that might be one thing. One big thing that we need to make sure that we understand, that we do not put charges in the final formula. So, examples of the first step should be pretty easy. Write the formula for the cation. And so magnesium is written as Mg with a 2+. Sodium is written Na with a plus. The second part of that is to write the anions. And I'm going to write the anions in, again, different colors so we can kind of see some things. Oxide is going to be 2-. And then with sodium, we're going to see that we have sulfide, which is an odd one, but it still does happen, with S with a -2. Now, the next part of this is that we're going to insert subscripts to show the number of each ion. If the charges cancel each other out, we don't put a subscript. If the subscript is a 1, you don't put a subscript. By writing the element itself is indicating that we are having the element there, as that is what we have. If there's more than one polyatomic ion present, we'll do examples of those. They need to make sure that that whole polyatomic ion is in parentheses as we write it. At the beginning of this, we'll actually put all polyatomic ions in parentheses, which is technically wrong. But when it comes to your assessments, you will need to not have the parentheses around our polyatomic ions unless that is necessary. So, examples of step 2. Well, we have our oxide and sulfide, and so we have our pluses and minuses, and so we have those already present. Oxide needs to have these written in there as well, and so what I see is that I have, oh, that's a sulfide, not an O, but a sulfide 2-. And so now when we look at this, we see that the charges for magnesium is a +2 and oxide is a -2. Those add up to 0. So when we write the full formula, we have MgO. Now, sodium sulfide is a little bit different. We only have one positive. That means we're going to have a charge of a -1, and we can't have charges in our final formula. So what we have to do is we need another sodium ion to cancel it out. And so now we can see from here that I have 2 sodiums and 1 sulfur or sulfide to give us the equation or the formula, and a 2 because it takes 2 of those sodiums. You always have to use the same elements present to cancel out the -2 from the sulfide. Now, the other method that can be used is known as the crisscross method. And it's always fun because you would always play the crisscross song because they want to make you jump. And so when we look at the crisscross method, it's an easy way to show this. This crisscross method is taught at the collegiate level in chemistry classes all the way down to the 9th grade physical science. And when I taught 9th grade physical science, you would see the crisscross method being used. Now, why would something so widely used be taught? Why would something be taught that much? Because it's easy and it works all the time. It's super easy as long as you understand to find the charges, at least find them on your periodic table or have them somewhat memorized, or by looking at the group number, a lot of times you can get that figured out. So the rules still apply. You write the formula for the cation. You write the formula for the anion. You insert subscripts to show the number of each ion present. If there's just 1, you don't write it. If it's more than 1, then you write it. Then that's what you do as you go through this. And we will show you a wonderful example in the next. So, aluminum oxide. Aluminum oxide. Aluminum, step 1, write the charge. Formula with the charge, 3 plus. Okay, I have oxide, O, 2 minus. Do my charges match up? No. So, what do? We need to crisscross the charges. Now, it's extremely important that we understand this one basic idea that usually comes back to get students. There are no charges in the final formula. So when we write this, the second part, we write out, that is not what I want. We write out, I'm going to keep the colors the same so we can see that. Now, what does this crisscrossing look like? Well, this 2 here gets brought down to the subscript. The 3 here gets brought down to the subscript of the oxygen. And so those numbers transpose, not the charges. The charges, they magically go away. They go away based on the rules of the least common multiple. Ultimately, that's what we're doing here in a very simplistic way. I always tell students that when they it's like when the Ghostbusters cross their streams, something bad happens. Well, that's what happens. The charges go away. And so it's good for chemistry. So the charges get crossed when you cross those streams. And so the 3 is seen by the oxygen. The 2 is seen by the aluminum. So we can, kind of in a way from this, identify where did that 3 come from. Well, it came from the positive 3 of aluminum. Where did that 2 come from? It came from the -2 of the oxide. And notice that I have no charges in the final formula. Another example, because this needs to happen. We really need to understand this. So we have copper 1 oxide. Copper 1 indicating that the charge on my copper is 1. It's a transition metal, so they have to tell us. So we have Cu+. Oxide hasn't changed. O with the negative charge. Now we need to do the crisscross method. I'm going to change those colors a little bit. So that's going to be there and there. And so now, here, I don't write the 1 on the oxygen, but the 2 on the copper has to happen. So we Cu 2 O. I don't write the 1 that would be subscripted on there by just writing oxygen. Indicates that there is one of those there. And that's what we have. Notice again, I have no charges in the final formula. Try a couple others out. Notice that we have something here. In this one, I can see that I have something interesting, and that is the ending of ATE. The ATE at the end indicates that I need to look on the back of my periodic table because that's a polyatomic ion. The how we do this still stays the same, in which I find the cation, Ca2+. The anion this time is a polyatomic ion, so I need to find that on the back of my periodic table, and I'm going to put it in parentheses just for the time being so we can help identify these, and it will also help us understand something here. And then we can see that this -2 here goes for everything inside those parentheses. So that -2 is for the whole sulfate ion. And when we do the crisscross method, but we don't have to because the charges cancel out, all we do is write this Ca. Now again, I'm going to use parentheses for the time being, SO4, as we have it there. So we can help identify that it's a sulfate and that's there. If we did the crisscross method, that 4 does not become 43 or 42 or whatever. So the crisscross method, that if we did not match up, the number goes on the outside of the parentheses. As we don't have that issue here, that's just what it will be. The more correct way of writing it would be writing it as CaSO4 without parentheses. Next one, iron 3 hypochlorite. Iron 3 means that I have a Fe with a 3 positive charge. It's written first, so it's a cation. Not only that, all of them are cations, especially if they're written first, and transition metals. Now what we have also happening here is we have again, a polyatomic ion with the ITE, but it has a prefix, so we need to be careful on which one we choose. So it's a hypochlorite. And so that one is indicating that I have, again, I'm going to put it in parentheses here, ClO. We'll put that in parentheses, but it has a negative charge. And we can see that my charges do not match up. So I need to do my crisscross method. In doing my crisscross method, I need to make sure that that 3 goes on the outside of the parentheses. That 1 goes to indicate that there's one iron there. Writing this all out again, we see that I have Fe. This time I have to have parentheses. Those parentheses need to be there. And so we have iron 3 hypochlorite. Now, if I did not put those parentheses there, I'm writing this in red because it's wrong, we would have FeClO3 like that. Well, that's a completely different thing. This polyatomic ion, ClO3, that's chlorate. That has different physical and chemical properties than hypochlorite. Because of that, they do not react the same. It's like putting sugar instead of salt in a pie, or putting salt instead of sugar in a pie. It's not going to taste good. I'm sorry. It has different properties, both chemically and physically, and therefore not going to taste the same. If you were putting this in a reaction, it's not going to work. It might not work, or you might not get the reaction that you choose. So doing it without the parentheses in this case is wrong. More examples. So we have aluminum sulfide. So aluminum, Al, 3 plus, sulfide, S, 2 minus. I see that my charges don't match up. I do the crisscross method. I write out my compound as Al2O3. No, not O3. Sulfide, not oxide. What's going on, Peterson? So, the next one, barium nitrate. Ooh, ends in ATE. That means it's on the back of my periodic table. So that means I need to look on the back of my periodic table to find out what nitrate is. The front of the periodic table is going to have my barium, Ba plus 2. Nitrate, again, I'm going to put them in parentheses at the beginning here. NO3, the negative charge. I can see that my charges don't match up, and so I do my crisscross method. And when I write it all out, I don't indicate the 1 on barium, I just write the symbol itself, but I do need, in this case, the parentheses there, and the 2 goes on the outside. Because if I didn't put the parentheses there, it would look like I have 32 oxygen, and that would be silly. The next one has a lot of things going with it, and that's because it has multiple polyatomic ions. We have ammonium, the only positive one. So I'm going to put it in parentheses at the beginning. And then I have phosphate. The 8 is usually the 8 and the ite, ITE and ATE, are usually the key indicators that you have a polyatomic ion. And where do you find your polyatomic ions? Well, for this class, it's on the back of the periodic table. From here, we can see that my charges don't match up. So when I do my crisscross method, I am going to have to use some parentheses again. And H4, 3 on the outside. I'm going to not put the parentheses around phosphate because it in itself is just 1. What is the correct formula for strontium nitride? Naming an ionic compound is the opposite. So we're going to use some of those things that we learned in the last half and look at going the reverse way. And so the way we do it, again, is 2 steps. That's how I kind of try to keep things. And then that's write the name of the cation, include the Roman numeral if it's a transition metal, and if you're not sure, always a good idea to look. So what does that look like? Well, for the first one here, we have Ca. Well, that's calcium. And that's all you have to do for the first step. Now the next one, I can see that I have Cu. No, you can't see me, but I can see you. Well, you can see me in class, but I can't. Well, now I can't see you now, but you can see me in class. But we're looking at copper, not Cu. Not the words sentences Cu. It's just Cu. Well, you get it. And so you have copper. And you might ask, which copper? This is usually an example that I even suggest having, is to write it down on a scratch sheet of paper, as into which one you think it is. Because then we're going to go and we're going to talk about how this is as we go through. So take a little bit of time, write down which copper you think it is as we move on. The second step is to write the name of the anion. Be sure to change the ending to IDE. So the step 1 is already done for us. It's calcium. Well, step 2 has us writing oxide. And that's it. And that's what you have. You have calcium oxide is what you have with CaO. So how do we go back to figuring out the copper? Well, we need to know what Roman numerals to use. We have to answer those questions. What is the charge of the sulfate ion? Well, it's a -2. It's always a -2, and that's very important that it's always a -2 because that's going to help us out, knowing that all the anions are going to have the same negative charge for that anion all the time. Sulfate is always going to have a -2. Chloride is always going to have a -1, and so on and so forth. So we have to look at that. We see what is the number or subscript written for sulfate. Well, there isn't one, so I wrote a little 1 there. And then I do the reverse crisscross method. You can kind of see how my arrows look. And now we ask that wonderful question. What number is written by copper now? Well, now there would be a 1 written there. Well, that indicates, because the 2 would be up here now, that indicates that I have copper 1 sulfate. Because that copper 1 knows because I have that little 1. That's where that 1 comes from. Because that's kind of, again, using our understanding of the crisscross method, where did those numbers come from? Well, in this case, that 1 came from copper. Where did that 2 down here come from? It came from the sulfate when we did the reverse crisscross. So that makes sense. And so we were able to use that and call this copper 1 sulfate. Let's do some more examples. Fe2O3. Now, I'm pretty sure a lot of you have this growing on your car, so let's use a similar color that would have that, because that would be oh so wonderfully awesome to increase that. So we have Fe is for iron. Which iron is it? Well, if we do the reverse crisscross, 2 goes up there, 3 goes up there, and now the 2 on the oxide, does that make sense? Yes, it does, because I looked on my periodic table and saw that it does actually make sense. So I can say that this is iron 3 oxide, also known as rust. Now the next one can be a little tricky, where I have TiO2. Well, if I do the reverse crisscross for this one, something is going to happen. I'm going to have the 1 that's not written there up to go up to the oxygen. The 2 goes to the titanium. And I know I need to write titanium in there. Titanium is a transition metal. I need to have it. But the 1 on the oxide doesn't make sense. That doesn't fit. It doesn't work for what we have or what we want. And so we have to wonder, how did that happen? What would be a reasonable explanation? Well, a reasonable explanation actually comes from the fact that it can reduce. And sometimes that happens, and that these will excuse me, these will actually reduce. And so what we have happening is that it reduces. Well, how could that happen? Well, what would be the multiple? Well, if I had a different number here, say I had a 2 and a 4, That 2 going to the oxide, that would make sense. The 4 going to the titanium, that would also make some somewhat sense. And so when I put it in the parentheses, I would have titanium 4 oxide. But you're going to have a tough time actually finding titanium 4 oxide on a lot of different things because you're not going to find it. You're actually going to find something else. And so what you're going to see then is that you're actually going to see 2 different types of naming, and this is where we get a little bit of confusion. We actually have what's called a common name. Well, the common name for this is not titanium 4 oxide. It's actually titanium dioxide, which I know is kind of difficult to understand. Well, I thought the monodiatride was only used for those, and you are correct. This is known as a common naming system. This is if you look on the back of your toothpaste or in the ingredients of a toothpaste tube, you're going to see titanium dioxide. You're also going to see titanium dioxide in the ingredients of paint. In paint, it's a binding agent. In toothpaste, it's used as a scrubbing agent. And they both have their uses. This is one of those weird examples that we have. I would accept both, but most people would only recognize titanium dioxide when looking at these problems. So let's get back to an example that makes maybe a little bit more sense. And so here I have one that I get to do the reverse crisscross. The 2 goes there. The 1 that's not written there goes to the chlorine. That makes sense. Oh, wonderful. It makes sense again. So I can have copper 2 chloride. Now, a very common mistake students make is when we say copper 2, we do have the Roman numerals there, and a lot of times students will usually use numeric versions of that, and that is technically incorrect, is that the Roman numerals are ways to indicate that. So it is something you do need to pay attention to as we move forward. More examples, because lots of examples lead us to better understanding. So we see that I have the sodium and the 2. I need to do my reverse crisscross. The 2 on the sulfate makes sense. So I have sodium, sulfate. Why did I not do the reverse crisscross for the sulfate moving up to the other? That's mainly because it's a 1. It doesn't really matter much. The next example, we have 2 numbers, so I'm going to do a reverse crisscross for both of them. And I see that it's AlS3, Al2, so the 2 goes on the sulfide. Does that make sense? Looking at my periodic table, oh look, it does. And so I have aluminum sulfide. The next one I have is we can see that we have manganese, and that's an odd one, and hypochlorite, and that's where we can see using the parentheses can be very nice, and it helps us identify our polyatomic ions. And so I have manganese, and it's 5 because if I do the reverse crisscross, I can see, oh look, that's where the 5 came from. So I have manganese, oops, wrong color, 5 hypochlorite. Now, some of these examples may or may not happen in nature, and that's because I don't want you to be able to Google everything. The next one, we see again doing a reverse crisscross. I can see that the 1 on the nitrite makes sense. That means the 2 goes to the barium. So I have barium nitrite. The correct name for CrCl subscripted 3 is... So hydrates have a little bit different naming. We're not going to focus a lot of time on them, but I think they are important as in that we do find them in our everyday life. A compound that contains water as a part of its crystalline structure, that means it's a part of the formula, is water of hydration. Most all compounds that we've been dealing with, or at least naming, are known as anhydrous. We do not actually indicate that they are anhydrous by name, just the fact that we don't have a hydrate added to it is usually that indication. We see these in the lab, but we see them every day of our lives, these hydrates, and they are a very important part of it. And so we're going to use this idea of water of hydration. Calcium sulfate is an example of that. It exists as a hydrate. It exists as a couple different hydrates. Very commonly seen as just the calcium sulfate, the anhydrous version of it. And then you have the calcium sulfate, and that's the hemihydrate, and that's where you have a half. Now, where does that half come from? Well, if you remember back in Chapter 1 on how the crystalline structure of these atoms occur, what you have is half of a water molecule in between that repeating pattern of the calcium and the sulfate. It's kind of in that middle. And so that's where we put the two or the half water, and it would take two of those repeating patterns to get, or actually show, that full water molecule. Whereas in the next one, it has where we have calcium sulfate dihydrate. The mineral that it applies to is actually known as gypsum. Now, this is the one that you would see in your everyday life, and you would probably have it in your house. It's known as gypsum rock, better known as sheetrock. And so we have those there. We do have to indicate. And so we use a mono, di, tri for the hydrate as a part of it. Here are some names and formulas of important acids. Some of these acids are acids that I am going to ask that you have memorized and are able to recall from time to time based on name and their formula. There are a few things that we need to understand is that the hydro indicates no O. So hydro means no O. So if you see an acid, and an acid will always have the H written first, and you have no oxygen present, that means it has the prefix of hydro. Not to be confused with the ones that have a prefix of hypo with a P. Those do have oxygen present. Most all of the group 7 elements form a hydro acid. Most of the other acids that we see will be ones that are formed from polyatomic ions. Now, most of the polyatomic ions have oxygen present, and that is why, if you notice, nitric acid does not have that prefix. Nitric acid is IX-R, 8s are icky. How do you know if something's icky? Well, you had to ate it. And that's kind of I know it's not the best grammatic thing, but that's what we use is 8s are ick or are icky. How do you know if it was icky? You ate it when you were young. Now, some of them also come from the other way where you have the ending of ITE, and that is the OUS. And how do you know that if it's ite? Well, you're just one of us. And so you have ite, us. And that's how we use that to kind of figure out how to use those two. Which one is it? How does it end? Well, if it's ite, You're one of us. So sulfuric acid, because it's ick, it's icky. How do you know? Well, I ate it. That's why you see the sulfate ion here in present. And now where did the 2 come from? If you did your reverse crisscross, it came from the sulfate, as you would notice. Carbonic acid, phosphoric acid. These are some very common acids that I ask that you know. They're common and they are found in our everyday life. And so we we need to know these as we continue on. Which of the following compounds is named correctly? The chemical formula for hydrochloric acid is the correct name for NH subscripted 4 OH is